All right, so this is the Unit 7 study guide. So I'm going to be referring up to this periodic table occasionally whenever we need that. So if you're working on this, it will help you to have that kind of ready. All right, so let's get started. First thing is we're going to talk about is an ionic bond. So that's kind of what we talked about last semester. So ionic bond is between a metal and a non-metal. So metal and a non-metal. Okay, what basically happens is basically a transfer of electrons, basically the anion's taking electrons from the cation. Okay, when it comes to formulas, we do not use prefixes. I know we just taught you prefixes with covalent, so just make sure we do not use prefixes. Okay, but one thing we also need to make sure is we are going to use Roman numerals. Okay, so whenever we see those transition metals that are in the middle, which we'll do some of those here in a second, we need to make sure we use that. So examples would be like, a simple example would be like calcium chloride, so like CaCl2. So if you look on your periodic table, you see that staircase right here. Okay, that's basically the dividing line. So on the left side, you have your metals. On the right side, you have your nonmetals. If it's ionic, that means you took something from over here and you took something from over here and put them together. Okay, when it comes to covalent, the way I remember that, and we'll write down our examples here in a second, the way I remember that is covalent kind of sounds like coexist to me. So that means that you found something from over here and you also put it with something from over here on the right side of that staircase. So let's go back and write some examples on that. So a covalent bond, that is just simply the sharing of electrons between atoms. Okay, so you're not really taking or giving anything. Okay, it's just kind of an overlap. And that is between a non-metal and a non-metal. Okay, on here we do use prefixes, and we'll go over those here in a little bit. So that's kind of like your mono, di, tri, tetra. Okay, so just make sure you only use prefixes for covalent. Okay, so a lot of times we see is as soon as we teach you prefixes, you want to use that for everything. Okay, we do not use it for ionic bonds. So examples would be something like SiF. Okay, so that would be like silicone monofluoride, and which we'll talk about here in a second, or something like CO2. Okay, so they're both on the right side of that staircase, so that makes them a covalent bond. Then it comes into intramolecular forces and intermolecular forces. So intra means within. Okay, that is basically what holds, so it holds a compound together. Okay, the way I try to think of that is it's kind of like a family. So think of a family as a compound. It's what holds the compound together. Okay, and so there are three of those. Okay, first one would be ionic, which we just talked about. Okay, second would be covalent. And third one is actually metallic. Okay, metallic is kind of like covalent, it's just the opposite. Now you basically take is a metal and a metal. Okay, now intermolecular forces, inter means between. And that is simply the bond or force between compounds. So that's what holds actual different compounds together. So if I had something like H2O, so here is H2O. What's going to happen is these H's right here on the end are going to be attracted to the O of another H2O. Okay, so you're actually holding those compounds together. That is intermolecular forces. There are four of those. We just kind of talked about those recently. You have ion dipole. Okay, your second one is a hydrogen bond. Your third one is a dipole-dipole. And last one, fourth one, is called London dispersion force. Okay, and we'll do more examples here, but it's better to see it when you actually start doing it. Now, when we're talking about IMFs, so we're talking about those intermolecular forces, we have ion dipole. Okay, that is just between, so that is the force between polar molecules in an ion solution. So I kind of usually try to think about salt water in this one. On our slides, we had a picture of like you had a sodium particle in the middle. And then basically what you had is you had all these polar water molecules attracted to that positive ion. So these that are going around it are just water molecules. Okay, it's not the best drawing, but you kind of get the point. Is what happens is basically these polar water molecules, which have the oxygen is negative, is attracted to that sodium ion. Okay, because the sodium ion is positive. Okay, so whenever you see like your Lewis structures, if you ever see something like AQ in brackets, that is telling you it's an ion dipole IMF. Okay, next one is hydrogen bond. Okay, hydrogen bond, that is when you have a hydrogen bonded to a nitrogen, oxygen, or fluorine. Okay, I just remember the name HNOF. Okay, sounds dumb, but it sticks. Okay, it has to be bonded to one of those three. If they're not bonded to each other, but they're in the same compound, it doesn't count. Okay, and we'll do some examples here in a second. So an example would look something like this. So this is actually NH3. Okay, what happens is one, I can tell this is polar because it's unbalanced. And if you look, I have a hydrogen bonded to a nitrogen. Okay, now if I had something like this, so say I had something like HCN. Okay, I have N and I have H, but they are not bonded to each other. Carbon's actually the one in the middle, so this would not count. Okay, our next one is dipole-dipole. Okay, dipole is basically the force between polar molecules. Okay, so basically what happens is when you have a compound or molecule that has a negative end, which makes it polar, anytime you have a positive or negative end or it's unbalanced, that makes you polar. If you have the negative end, it's going to be attracted to, or vice versa, the positive end of another polar molecule. Okay, so that is what dipole-dipole means. So if you had something like oxygen and hydrogen, which makes H2O, oxygen is technically more negative, hydrogen is going to be more positive. Okay, so if I have another H2O over here, okay, and each of these H's are positive and this O is negative, this oxygen is actually going to be attracted to that polar end of that water, and it just keeps kind of that domino effect. Okay, London dispersion force, this is basically something that pretty much all of them have. Okay, this is just the attraction force. Okay, so it's just the force between the nucleus of one atom and the electron of another atom. So basically what that's saying is that all these compounds or atoms in their nucleus, they have protons which make them more positive. Okay, they're going to have some type of attractive force to electrons of surrounding atoms. Okay, now it's very weak and it may not be enough to actually steal an electron stuff, but there is an attraction force there that kind of holds them close together. Okay, so that can be for both polar and non-polar. Okay, van der Waals forces, those are basically everything besides ion dipole. Okay, so van der Waals forces are just basically the general weak IMFs. Ion dipole would be the strongest, so as you go up, okay, it gets stronger. Okay, so ion dipole will be the strongest, then it gets a little bit weaker with hydrogen bond, dipole gets a little weaker, and then the weakest of them is the London dispersion force. So the ones that make up your van der Waals is your London dispersion force, dipole, and a hydrogen bond. Okay, ion dipole is kind of like in its own category. So if you were talking about van der Waals, it would just strictly be these three. Okay, let's move on to the next part. We have Vesper Theory. So Vesper Theory just actually stands for valence, shell, electron, pair, repulsion. Okay, kind of keyword there is repulsion. Okay, whenever you have these atoms that make up a compound and they attach to that central atom, they don't like each other. So basically what they do is they repulse each other, and so they want to get as far away from each other as they can, which leads to an escape. Okay, so it says describe the main idea of Vesper theory. Okay, is that basically these terminal atoms, are repulsed by each other. And they want to be as far from each other as they can. Okay, so again, terminal atoms can be repulsed, are basically repulsed by each other, and they want to be as far from each other as they can. Now, it says describe what it does. So when they actually do get as far from each other as they can, what it does is it creates a geometric shape. Now, our keys may be a little bit more in depth, but for the sake of time and stuff, I'm just trying to give you the general idea of it. So if you ever want more information, you can look on our keys or even look it up. Okay, so let's move on to the next section. Section is going over Lewis structures and geometry. So just some of the base things is central atom. So the one that is the central atom, okay, who's going to be in the center, is the least electronegative. So electronegativity, remember we talked about that last semester. It's basically the ability to steal an electron. So you want the one that does not want to steal as much in the middle. Okay, you do not want the one who wants to steal in the middle. So the way I try to remember that with my class is you want the furthest to, or you can say furthest from fluorine, because fluorine is the most electronegative. Or I just tell a lot of my students is just pick the one that's further left on the periodic table. Okay, it will never be hydrogen or fluorine. Okay, so hydrogen will never be in the middle, fluorine will never be in the middle. Okay, so your central atom would just be like here you have, let's just say CCl4. Okay, central atom is just that carbon right there. So terminal atom. Terminal atoms, that is the atoms that surround the central atom. So not a whole lot to know there. That's basically, if I took the same example, this chlorine right here would be a terminal atom. So central would be the center. Okay, terminal is going to be the outer. Okay, lone pairs. Okay, so it says non-bonding pairs, unshared pairs. Basically, it's anything that's left over that's put back on the center. Okay, so they are electrons on central atom, and they are not shared. So remember when we drew a Lewis structure, say I use this example, well, I'll use a different one, the one that actually has leftover pairs. Let's go back to that NH3. Okay, I had this leftover pairs once I drew Lewis structures right here. Okay, so that is a lone pair. So if I asked how many lone pairs were on this example, you just tell me one. Okay, when you see this line right here, that is actually a shared pair of electrons. When you see the pair of dots, that means it is not shared. It's called a lone pair. Okay, now polarity we just already kind of talked about a lot, quite a bit, just a while ago. Polarity just means polar or non-polar. Okay, if it's polar, that means it's unbalanced. That means that it's not all even on your terminal atoms. Something's thrown off. There might be lone pairs that are throwing it off. Okay, it's something that's not necessarily symmetrical. Versus non-polar means everything's balanced out. There is no kind of leftovers. Okay, throwing it off. There is no imbalance. Like if I were to look at my examples over here on the right, like this CCl4, that would be non-polar because it's just 4 chlorines surrounding it. There's nothing throwing it off. It's nice and symmetrical. It's balanced. But if you look right here on the NH3 we just did, that would be polar because I have 3 H's in that leftover pair right here. Okay, that leftover pair is what's throwing it off. If there are 4 H's around there and no leftover pairs, then it would be non-polar. But that is throwing it off, which would make it polar. Okay, electronegativity, we just talked about that. I'm going to kind of skip over that. Electronegativity is just the ability to steal. So you want the one in the middle to be the least electronegative. Electron domains, that basically just means the number of attachments. Oop, let me go over. It's basically the number of attachments to the central. So if I go back to my example, so I have CCl4. And and ask you how many things were attached, you would just tell me 4. Okay, now if I went back to the other example in H3, okay, when I draw these, I like to circle these leftover pairs just because it helps me remember they're there. Okay, lone pairs on the central do count as attachments, so this one would also be 4. Okay, so you cannot forget that lone pairs count as an attachment. Okay, now electron domain geometry, the way I try to explain it, it's kind of like your base shape. It's just your base shape that's determined by the number of attachments. Okay, so you got things like, and we'll go over your shape sheet here pretty soon. Okay, and hopefully that'll have you ready. So I would have that ready whenever we're doing the Lewis structures. Okay, so we have things like linear. You have things like trigonal, planar, and then we'll move on to the next part. So molecular geometry, that is a more defined shape. Okay, so a more defined shape. Okay, that deals with attachments, like how many, if there's leftover pairs, if there's no leftover pairs, and we'll do quite a bit here in a minute. So we'll go over that. Formal charge, this is just kind of a bookkeeping method. To account for valence electrons. Now, if your teacher uses this method more, that's totally fine. Whenever we start doing Lewis structures here in a bit, if there's a way that you do it and it works every time, by all means, stick with it. Okay, I'm going to show you kind of my method, and if that works for you, awesome. Okay, hybridization, we actually left that off on this unit, so I'm not going to skip over that part. Let's move on to the next section. So rank IMFs, intermolecular forces, from strongest to weakest. Okay, so we kind of did that a little bit. Get my key. Okay, so we had our strongest. Oops. Our strongest was ion dipole. Okay, so that was the one where you actually saw like the little AQ on your Lewis structure. Then the next, it's getting a little weaker now, so strongest was ion dipole. Okay, a little bit weaker is going to be the hydrogen bond. Okay, that's when you have an H bonded to an N, O, or F. All right, getting a little bit weaker now. Then now you have your dipole, and that is for polar, just polar molecules. And then your weakest one would be your London dispersion force. Or you can just label it LDF. Okay, that is for non-polar or polar. Okay, in general, how do IMFs affect the physical properties of a substance, such as boiling point and melting point? Is basically the more of these you have, so the more IMFs you have, the stronger the bond. Now, when you have a stronger bond, that's going to take more heat or more energy to break that up. Okay, so if I had something that had ion dipole, or as I go up this list, the more of these I have, or the higher I go up, the higher the boiling point, the higher the melting point. Okay, so London dispersion would be very weak, wouldn't take very much energy at all, so it would have a low boiling point, versus something that has London dispersion, dipole, and hydrogen bond. Okay, that's more bondings, which would take more heat, so that means it's going to have a higher boiling point, higher melting point. Now, order the following substances from lowest to highest boiling point: carbon dioxide, dihydrogen monoxide, and phosphorus trihydride. Okay, so basically the way to do this is to look at the Lewis structures. So I'm just going to draw them out. I'm going to go over how to do Lewis structures in a minute. Okay, so I'm just going to draw you the Lewis structures for right now so we can see. So I'm going to look at carbon dioxide. Okay, carbon dioxide actually looks like this. Okay, then I've got dihydrogen monoxide. Okay, so that basically, that's a fancy word for H2O. Okay, so we've got H2O. So O is going to be in the middle. And then you got two H's on the side. Okay, and then your last option is phosphorus trihydride. Okay, so that means I got phosphorus in the middle, and I'm going to have 3 hydrogens surrounding it. And I got a leftover pair. Okay, so basically what I'm going to do is I'm going to start looking at what IMFs do each one have. So if I look at CO2, okay, this looks nice and balanced out. If I refer to my shape sheet, I only have 2 attachments, and that's linear. And if you look, both oxygens are the same, so this is balanced out. So this would actually be nonpolar. Now, since it's nonpolar, the only IMF it's going to have is London dispersion. That's it. Okay, I cannot go from London dispersion to, so if I go to a different ink, so refer back up to here. Okay, I start at the bottom every time. So I'm going to start at London dispersion. Is it nonpolar, polar? Either one, it's going to have LDF. Okay, so I've at least got that type of bond going on. My next step is to go up. Okay, is it dipole, dipole? Well, in order to be dipole, dipole, it has to be polar. Okay, this is not polar, so that means I have to stop. Okay, let's move it on to H2O. Now, even though I drew this where it looks symmetrical, if I actually drew it the right way, it's actually on your shape sheet. It's actually called bent. Okay, because basically those hydrogens being pushed away, and it creates a bent shape. And so you have this negative region over here, and then you have this positive region over here. Okay, so that is going to be considered polar. Now, since it's polar, I know it has LDF, London dispersion, because it's nonpolar or polar. Now, since it's polar, I also have dipole, dipole. Now, my next option is hydrogen bond. Hydrogen bond is, do I have an H bond into an N, O, or F? Yes, I do. So I also have a hydrogen bond. So that means it's got all 3. So that means it's pretty strong. Okay, let's look at the next one. Okay, this one would be this is polar because this is throwing it off. So it's polar. So it's going to have LDF. Okay, at least got that. Now, since it's polar, it now has dipole, dipole. Now, in order to be a hydrogen bond, it has to be an H to an N, O, or F. Okay, so I have H's, but I don't have either the N, O, or F, so I have to stop there. So if I were to rank this from lowest to highest boiling point, lowest would be CO2. All it has is that LDF. A little bit higher would actually be my pH 3. Okay, because I have 2 of the IMFs. And then the highest boiling point would actually be my H2O, because I've got all 3 types of bonds. Okay, going on to complete the following table, we're looking at naming, so I'm not going to go through all of these, but it'll actually help do prefixes first. Okay, so for covalent, okay, we use prefixes, so you have mono for 1, di for 2, tri is for 3, tetra is 4. Okay, the way I use it with my class is if you ever play the game Tetris, all your shape possibilities have 4 blocks in it. Okay, so that kind of makes sense for Tetris. Okay, 5 is penta. That's like the pentagon. 6 is hexa. I remember this because 6 has an X in it, and so does hexa. Then it goes hepta. So it goes hexa, then hepta. That's 7. 8 is octa. 9 is nona. And 10 is deca. Okay, so remember there are 10 years in a decade, so if you need help memorizing that. Now we can use those to come back up here. So I'm going to figure out, is it ionic or covalent? So ionic is basically if you have something that's a metal and a non-metal. Okay, so potassium, if you looked on your periodic table, has K with a +1. So remember, if you need to go back through your charges on your periodic table, remember it goes +1, +2, +3, plus or minus 4, -3, -2, -1, 0. Oops. I have no idea what I did there. All right, so let me fix this real quick. And then you have 0. Now, in your middle group, you have your transition metals. So remember, silver is always a +1, zinc's always a +2, aluminum's always a +3. Basically, anything else from here all the way to the staircase is a transition metal, meaning you would need a Roman numeral to tell me what that charge is. Or if I gave you a Roman numeral, I'm telling you what the charge is. Okay, so let's go back. So potassium was K with a +1. Hydroxide is on your polyatomic list. That is OH with a -1. So I can see that those are balanced, so I'm just going to put KOH. Okay, and by molecular, I just mean covalent. So you can actually just cross that out. So since I have a metal and a non-metal, that is going to be ionic. Now N2O4, if you looked on the periodic table, okay, N is on the right side of the periodic on the right side of that staircase, and so is oxygen. Okay, so finding charges would not do me any good. So like a -3 here or a -2 here is not going to do me any good. Okay, because I don't need to balance them because I basically told you how many are already there. So 2 nitrogens, so I'm going to put dinitrogen. Okay, then oxygen, I've got 4 of them, so that's going to be tetroxide. Okay, now if you put tetraoxide, that's fine. Technically it's tetroxide. Just please make sure you're still ending that last one in IDE. Okay, and this would definitely be covalent since we're using prefixes. All right, FeCl3, so I have iron, which is a metal. I don't know the charge of it, okay, because it's a transition metal. But chlorine, I know chlorine's always a -1. Okay, if I have 3 of these chlorines, that means this is a -3. So iron would have to be a +3 in order to be balanced out. So, and if I were to write the name, I would write iron 3, because that's the charge of my iron. Instead of chlorine, I'm going to put chloride. Okay, and this is ionic because you have a metal and a non-metal. Now, ammonium sulfate. Ammonium is NH4, because that's on your polyatomic list with a plus sign. And sulfate is SO4 with a -2. So this is actually ionic because, and technically in order to be an ionic, it's a positive and a negative. Okay, but in this case, ammonium is not going to be a metal. Okay, so we're not going to try to throw you off with that kind of stuff. And also, I couldn't use prefixes on this anyway. So I have ammonium with a +1, sulfate with a -2. So that means I'm going to need 2 ammoniums to be balanced out. So it'd be NH4. I need 2 of them, so make sure you put in parentheses. And then you can put sulfate, SO4. All right, carbon tetrachloride. So dead giveaway, this is covalent, as I already see a prefix. Okay, so this is covalent. So carbon, if you notice, we will never use mono on the first one. Okay, so if carbon, it just says carbon, that means there's only 1 of them. Tetra means 4, so that means there's 4 chlorines, so this would be CCl4. SF6, okay, so sulfur and fluorine are both on the right side of that staircase, so that's covalent. Okay, so remember, we don't use mono on the first one, you can use it on the second one, but I'm not going to say monosulfur, it's just sulfur. Okay, then F6, so that means I have 6 fluorines, so that becomes hexafluoride. All right, I'll do one more and then we'll move on. Okay, so lead 4 oxides, remember this is a 4. Now that does not tell me how many leads I have, it just tells me that lead is Pb with a +4. Oxygen is a -2. Okay, now you could do crisscross if you wanted to, so you could say Pb2O4. Okay, but that wouldn't really make sense because you can reduce it. So if you can reduce it, please reduce it. So your actual formula is PbO2. So this would be ionic because that is a metal and a non-metal. Okay, let's move on. So sigma and pi. So sigma and pi, it does not take very long to go over. Just got to make sure you remember what counts for what. Okay, a single bond, so meaning just a line, would equal 1 sigma. Okay. A double bond would be 1 sigma and 1 pi. Okay, a triple bond would equal 1 sigma and 2 pi. So if you notice, there's always at least 1 sigma. So single sigma. Okay, double is when you, triple is when you start adding pi. So if it's double, you just add a pi, and then triple, you add 2 pi's. So when you're counting these, just be careful. Okay, when you do this, is I like to count things when I like to mark things as I go. Okay, so like if I were to count singles, like I would just go through and I would mark each one just because these can get a little confusing. And on the test, we probably won't give you something like this where you can get lost. But if you just kind of check mark each one, that kind of helps you not get lost. So like a single would just count as sigma. So I go through and count all my bonds, whether it's single, double, triple, and that'll tell you how many sigmas there are. In this case, there end up being 30. Okay, then I go through, are there any double bonds? Okay, so I have a double bond here, double bond here, double bond here. I believe that's it. So I have 3 double bonds. So if I look over here, double bond, each double bond counts as 1 sigma and 1 pi. Well, I've already done my sigmas. Okay, now each double bond counts as 1 pi. So that means this would be 3 pi. Okay, so something like this one right here is probably a little easier to do. So if you count each one, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That means there are 15 sigma bonds. Now pi, only thing I have to worry about pi is a double or triple. Well, I only have a triple bond right here. So that would just be 2 pi. And that's basically it for that part. All right, so what I'm going to do is I'm going to pause this video. I'm going to do a kind of a part 2 because I need to attach that shape sheet that kind of helps out with this. And then you can move on to the next video if you need help with that.